The last set of characteristics we need are for the brain, and the brain is going to have again a permeability. Let's put my pen wrong. Permeability of mu naught. There's no magnetic material here, folks. No spinning electrons causing spin, causing the magnetic field. Okay, the dielectric constant is going to be 55 times epsilon naught. The conductivity is appreciable in the brain, and we would expect it to be because it's salt water, is 1.6 Siemens per meter. The characteristic impedance is 50 ohms at an angle of 0.1 degrees, which is approximately 50 ohms. And the attenuation constant, which we really do care about for the brain because we're dissipating this energy in the brain, and that's what we're trying to figure out. If I went through and calculated the numbers as they actually stand for a lossy dielectric, I'm going to get that to be 1 over 25 millimeters. Instead, for my calculation, I'm going to include some margin of error, and I'm going to assume the skin depth, so the characteristic length for a metal, the attenuation constant for a metal, and that's approximately equal to 1 over 9 millimeters. So what does this mean? That means that I'm going to dissipate more energy per length per unit volume than I would for the actual conditions of the brain. My two assumptions that I'm going to make in this video as kind of fudge factors to make sure I am doing a sensible calculation. I'm going to, over here on the left, I'm going to double this power that the cell phone radiates to 4 watts, so it's more powerful than anything I found on the web, and I'm going to use this skin depth. I'm going to, instead of using the absorption coefficient, the absorption constant, the attenuation constant for the lossy dielectric, I'm going to use the skin depth for metal. Okay, I hope that's clear. I'm using those two assumptions to make this a more worst case scenario. Okay, I need a model of the cell phone and how it radiates its energy. I'm going to draw here a cell phone. I looked up some dimensions of the iPhone, the new iPhone, the one with Siri, on the web. Let me go down because the dimensions will look funny otherwise. Okay, there's my 3D phone. This dimension here is about 115.2 millimeters. This dimension is 58.6 millimeters. The user is over here, the brain. I'm going to assume that we can divide the cell phone into halves, like this. And there's 4 watts total. I'm going to assume 2 watts go this way and 2 watts go this way. Probably the way the antenna is designed, most of that energy is going to go this way, away from the user's head, but let's assume that it is going this way. Let's assume that 2 watts hurtling towards the user's head is uniformly distributed over this area here as a plane wave. What is our power density there? And that's going to be the calculation of the power, well, let me run through the area. So the area, that area up there is approximately equal to 59 times 10 to the minus third meters times 115 times 10 to the minus third meters times 1/2, because it's half of that area. Okay, and that's going to be approximately equal to 3.4 times 10 to the minus third meters squared. What's our power density? Well, it's just going to be power divided by area. That's going to be 2 watts divided by this 3.4 times 10 to the minus third meters squared, and that comes out to be approximately 588 watts per meter squared. And I'm going to make all sorts of assumptions, or simplifying assumptions, or rounding assumptions. So I'm going to say this is about 588. You can do the calculation. That's what I calculated it as. What is the electric wave? Because remember, our reflection and transmission coefficients only apply to the electric field, the impinging electric wave, not power per unit area. So power in watts per meter squared equals, remember that analogy I drew to the resistor? Okay. It's electric field in terms of volts per meter, electric field squared over Z naught. And our first medium, Z naught, is 377 ohms. This term here we just calculated as 588. So the electric field in terms of volts per meter is going to be equal to 588 divided by 377 quantity squared. What does that come out to be? That comes out to be 470 volts per meter. A wild mistake here, folks. Let me backtrack. I should not have divided, and that makes it look very strange. I made a glaring error. This is the electric field is going to be the square root of 588 times 377. Apologize. And that does come out to be 470 volts per meter. Okay. I'm going to make a side note here. Side note. I have assumed that the impedance of free space, Z naught, equals 377 ohms. Is that a fair assumption? Well, that's only a fair assumption for the far field. Far field. What is a far field? And by extension, what is a near field? Well, let me draw a little model here. If we had some object that's radiating, and we go out in the distance and draw a line, we're going to say everything on this side of the line is the far field, and everything on this side of the line is the near field. What is the near field? Well, the near field, sometimes called the reactive field, is the portion of the electromagnetic field that if you were to interact with it, the source would react. So if you were to take energy, power from the energy per unit time, or power from the field in this region, the source would have to pump harder to maintain whatever electric field is around there. However, when you're in the far field, this is the case of, say, photons, where the energy is radiating and it's completely independent of the source. If you were to interact and collect the photons, collect the electromagnetic radiation out here, the source doesn't react to that at all. There is an approximation where this distance, or the divide between the near and the far field, is lambda over 2 pi, where lambda is the wavelength. Let's see where I am in terms of whether I'm in the near field or far field. So in my case, I'm dealing with 1920 megahertz, 1920 megahertz. And we know that the speed of light in a medium, and in this case it's free space, equals the frequency times lambda, okay? We want to find lambda. So lambda equals c over mu, 3 times 10 to the 8th meters per second over 1920 times 10 to the 6th, 1 over second, and this is going to come out to be about 0.16 meters, okay? So what's lambda over 2 pi then? Lambda over 2 pi is approximately equal to 25 millimeters. I'm going to call that good enough that we can use 377 ohms rather than some other value. This is primarily an electric field radiation, so the characteristic impedance is going to be higher than the 377 ohms when you have it pressed right up against your ear, but I'm going to assume that we can use the 377 ohms because I don't know what the other characteristic impedance would be for this, and I don't think it's very easy to calculate given the amount of unknowns we have with the cell phone. Actually, I want to note that since I think we're dealing with the case of a cell phone radiation, primarily electric field radiation, the Z of the medium between the cell phone and your scalp, or the air, would be greater than 377 ohms. And the reflection coefficient then would be Z2 over Z1 over Z1 plus Z2. In the case I'm talking about here, this term would be large, and this term would be large. This would be Z1. And our reflection coefficient, if anything, would be larger than what I'm going to calculate in this example. Okay. I think I've stated the case, the simplifying assumptions, and we're going to go ahead and do the calculation in the next video.